We've looked at weak acids and weak bases, and we know that we can write an equilibrium expression for these two types of equations because they do not dissociate or ionize completely, so they're in equilibrium with the water. So let's look at how they relate to each other. So Ka times Kb equals water. And here's the proof. Now, the first thing I want to tell you is that a lot of people think if I go this way, it's the acid, and this way, it's the base. But you see there's really no OH here. So they are two separate equations, and these two reactions are happening at the same time in water, and our water equilibrium is established, and our water equilibrium is the concentration of H plus and the concentration of OH minus multiplied together always equals 1 times 10 to the negative 14th. So when I take these two different but related reactions and I multiply them together, I will get water because you can see my species, my negative anion, and my acids cancel out, and I'm left with my hydroxide times my hydrogen ion or my hydronium ion multiplied together, which is Kw, which is 1 times 10 to the negative 14th. Okay? So we are going to explore Ka and Kb and how they're related and how you can calculate them. But I want to show you this. Here is our acetic acid, and it's dissociating. And here is our acetate ion, which behaves like a base, and it's dissociating. Okay, so now if I put acetic acid into solution, both these reactions are going to happen. And so which one will drive farther to the right? So which will we have more H plus in solution, or will we have more OH in solution? Because this is a weak base and that's a weak acid. So what we have to do is we have to compare our Kas and Kbs. If we have a larger number, remember it is products over reactants, it means we have more products. So here our Ka is greater than our Kb, so that means that we will have more H plus in solution than we will have OH, and that makes this solution acidic. Okay, so remember these are two separate reactions, and we have to see which equilibrium lies farther to the right, and that will determine if we have more H pluses or more OHs. If we have more H pluses, we're going to be acidic. So now I'm going to talk about finding the pH. Now, this is very easy. If we have a strong acid, strong base, it's going to dissociate completely. So if we have 5 moles of hydrochloric acid, we'll have 5 molarity, or moles in a liter, we'll have 5 molarity H plus concentration. Okay, here I have H2SO4, so when this dissociates, it's going to dissociate into 2 H's, so I will have 10 molar H plus. And if you guys want to write an ice chart with this, you can. I think it's easier just to figure it out directly. But either way, you will see some keys that do an ice chart here, okay? And really, that's just how this breaks apart into water, and it will break apart into 2 H plus ions. So if I have a 5 molar solution of sulfuric acid, my molarity for my H plus ion is 10 molar because there's 2 H's, one, for each, okay? So same with sodium hydroxide. What's my concentration of my hydroxide ions? That's 5 molar because I started with 5 molar. But calcium hydroxide will break up into 2 OHs, so 2X. So 5 molar will go into a 10 molar OH concentration. And remember, if we have OHs, we need to convert that to H's and then to pH. Or you can convert it to POH and then go to pH. Okay? So this is what we're going to work on today. And our next lesson is going to go about figuring out the pH for our weak acid or weak base, and then we do need our ice chart to see how it's going to dissociate, and because we don't know how far it's going to shift. Okay? And our final lesson on pH calculations will be about reaction. And if we have a strong acid or a strong base, we basically have a BCA chart where we're doing moles, and we do a limiting reactant chart. What's left determines the pH. So we need to change moles to molarity, okay? Because in our chart, for our BCA chart, we're going to figure out moles, but it's our molarity that determines this concentration, and we have to figure out moles in total liters. So remember, it's total liters of solution, not just one or the other. And we'll go through examples of this. Okay, so this is our limiting reactant. Once we find out how much of our acid is left, we can find that H plus concentration, or how much base is left, we can find that OH concentration. And reactant, I want you to think about this like Pac-Man. If I put in one H plus and one OH, the H is going to eat the OH, it's going to turn into water, okay? If I put in two H's for one OH, my H is going to eat the OH, but then I still have one more H left, and that's our limiting reactant. So think about it like Pac-Man. It's eating it up, reacting, and it's disappearing. But once it eats it all up, I might still have some left. So that usually helps people understand what's going on here. Now, if I have a strong with a weak, we need to do two steps. First of all, my acid is still going to eat the base. So this is a regular stoichiometry. Even though it's weak, they still react stoichiometrically. Okay, and we need to see how many moles is left. Okay, so if a strong acid or base is left, it's going to completely ionize, and you can convert that molarity to the concentration of H plus or OH to get the pH. If a weak acid or base is left, it's going to be in an equilibrium, and you need an ice chart to figure out the molarity of the H plus or the OH. So that's an overview of the type of reactions that we're going to be doing, and we will go through examples of each one, and we'll be breaking this down into steps.